Elastic scattering. It's
available.
Yes, I'm here.
Please share your screen.
Okay. I need to wait for, yeah, now I can. Can you see my screen?
Yes, go ahead, please.
Okay, thank you, Craig. So I would like to thank the organizers, and as my title suggests, I will talk about pion and kaon generalized partial distributions. So a brief introduction is that, as you know, QCD is characterized by two emergent phenomena, not obvious from the Lagrangian. One is confinement, and has to do with the fact that its fundamental degrees of freedom, namely quarks and gluons, are not isolated in nature. They form hadrons. The other is the dynamical generation of mass. Quarks and gluons acquire mass dynamically inside hadrons. So it is typical to compare the mass given to stray-like quarks from the Higgs mechanism to the mass of the proton. And as you see, about 99% of the proton mass comes from the QCD's interactions. So naturally, these phenomena are tightly connected with the QCD running coupling. In our modern picture of the coupling is that it exhibits the well-known ultraviolet fall, but in the infrared, it raises and saturates at a fixed point. The connection between both domains is smooth, and somewhere in the middle, in the transition domain, we can define the so-called hadron scale. This is the scale at which the fully dressed valence quark, like treated as quasi-particles, express all the properties of a given hadron. This will become important in next slides. So the study of, I will say the study of pion, proton, and kaon is crucial in order to understand the emergence of mass in the Standard Model. For instance, the pion and proton masses are dominated by QCD dynamics. QCD simultaneously explains the massiveness of the proton on the masslessness of the pion. However, if you take the pion and replace the antiquark by a strange antiquark, you will see an interplay between the Higgs and the strong mass generating mechanisms. So in this talk, I will focus on this pion and kaon and compare their structural properties. The properties of a given meson are encoded in the beta-salpeter wave function. Projected onto the light front, we can obtain a whole bunch of information via the light front wave function. So the idea is to compute everything in quotations from the light front wave function. And we can start, as we usually do within the Dyson-Schwinger equation formalism, with solutions of the quark gap equation and the meson beta-salpeter equation. And in fact, there are already several works concerning parton distribution amplitudes, parton distribution function form factors, and so on. So we can, in principle, attack this problem following this path. However, we will follow an alternative, and I will say more economic approach, which is model the beta-salpeter wave function in some way that I will be able to reproduce non-results on the PDA and the PDS. So let's start with this. We take the pseudoscalar meson beta-salpeter wave function, and in an Nakanishi-like representation, this is written in terms of a matrix structure, the product of three quadratic forms in the denominator, and the Nakanishi weight. For our purposes, we can retain only the leading beta salpeter amplitude in this matrix structure. The leading term adopts this form, and this is 1 from a total of 4. So the denominators will allow us to follow certain steps to obtain algebraic or semi-algebraic representations. And the spectral weight will, of course, be connected with the meson properties. So recalling the expression for the light from wave function, we have the beta salpeter wave function and the projection onto the light front. If we integrate on powers of x, we will have the melting moments, and following a series of algebraic steps, namely Feynman parametrization, changes of variables, rearranging of the order of integrations, we can identify the light from wave function for a given meson in terms of the spectral density. This density will determine the meson properties. But it will also work the other way around. For instance, the connection between the light from wave function and the PDA is given by this expression. And on the right-hand side, we have the connection with the Parton distribution function. So if I use known results for the PDF and the PDA, I can provide a sensible form for the Nakanishi weight. And this is what we do in practice. So being more explicit, this is a light from wave function, and it is written in terms of a series of integrals along the Nakanishi weight and a Feynman parameter. In the denominator, I will have some sort of quadratic form in which this series of terms appears. So this term over here can be understood as a constituent mass for the valence quark. This is a parameter, a mass scale parameter. This is the difference between the quark and anti-quark masses and the meson mass. So our experience tells us that this representation for the light for the Nakanishi weight and these parameters over here are sufficient to reproduce known results from Dyson-Schwinger equations formalism. I will show it later. At this point, what I would like to stress is that if we take the chiral limit, this term over here vanishes, this term over here vanishes, and now taking this scale lambda to be the same as the constituent mass of the quark, we arrive at a very, very simple model. So in the chiral limit, the Nakanishi model reduces to this expression. So the light from wave function can be written in terms of the distribution amplitude or in terms of the distribution function. Moreover, we arrive at a factorized version of the model because the square of the PDA is equal to the PDF. This will be a sensible assumption as long as we remain close to the chiral limit. So this simple model, this simple factorized model, will produce identical results as the Nakanishi model for the pion. So we arrive at a close expression for the light from wave function. So at this point, unless specified otherwise, I will show results concerning the Nakanishi model. But for the meantime, I would like to do a little bit more of algebra to show you the following. This is the chiral limit model. One thing that becomes evident is that we have an extra power of paper. This is a wrong asymptotic behavior. So this simple model can be improved as follows. We add a term which has the correct power law, asymptotic power law of paper, and with some weight gamma. This will be equivalent to having the two most dominant beta salpeter amplitudes. So at first, we only had the leading Bethe-Sapir amplitude. Now it's like having the second one. Okay? So coming back to the Nakanishi model, this is what we produce. Pion and kaon light from wave functions are on the left. And after integrating out the k-pair variable, we arrive at these distribution amplitudes. So distribution amplitudes, blue for the pion, in red for the kaon, have a smooth endpoint behavior. They are dilated with respect with the asymptotic form as a result of the emergence of hadron masses and dynamic alkaline breaking. And in the case of the kaon, we see a slight asymmetry. This is the effect of the mass difference of the S strange and EU quark. So this is the effect of the interplay with the Higgs-induced mass generating mechanism. Now, we can also obtain the GPDs. In the overlap representation, we can have the GPD with this expression, which is valid so long as we restrain ourselves to the declared region. There are sophisticated methods to extend it to the ERBL region. We won't follow this at the present time. This expression, this overlap representation, is known to be compatible with the diagram approach, so it's okay. And in the case of the Chiral limit models, we will have analytic expressions for the GPDs, which are depicted here for the pion and for the kaon. The first thing we can compute from the GPDs are, of course, the PDFs, because this corresponds to the forward limit, namely the t=0 slice. So over here in blue we have the pion, and in red we have the kaon, and we compare with a parton-like profile in black. What do we see? Well, as the PDA, we have a smooth endpoint behavior, of course, with the proper power of 2. The distributions are dilated with respect to the parton-like profile as a result of dynamic chiral symmetry breaking. In the case of the pion, we have a 50-50 share of the total momentum, while for the kaon, the U quark has 47% and the S anti-quark has 53%. So this asymmetry is again a result of the Higgs interplay with the QCD mass generating mechanism. Importantly, this picture is valid at the so-called hadron scale. As I specified before, this is the scale at which the meson properties are completely given by the fully dressed valence quark. QCD evolution undresses the valence quarks and generates gluon and C. Here in the left, I show results concerning the pion PDFs. In blue, we have the valence. In green, we have the gluon. And in red, we have the C. I have to mention that in this case, the initial scale for the evolution is the so-called hadron scale. So this is not a free parameter, but a scale that it is determined from some place, in this case from the QCD running coupling. And what we see is that we obtain agreement with this known analysis from ASB, with the lattice cross-section results, and by construction with the Dyson-Schwinger equation results. And here in the right, I just compare the valence C and glu of the kaon and the ratio with the pion. One can notice from these momentum fractions over here that at the experimental scale corresponding to 5.2 GeV, the valence in the pion is 41%, while the valence in the kaon is 43%. Again, this small difference is a consequence of the S quark in the kaon. Other things that we can obtain are, of course, the form factors. Form factors can be obtained from the evolution with the variable t of the moments. and the zeroth moment corresponds to the electromagnetic form factor. In this case, we compare our result in blue with Dyson-Schwinger equation result in red and with JLab experiments. So the agreement is fair, and this this corresponds to the Nakanishi model result. Now I would like to show the chiral limit model result, which corresponds to this simple expression that accounts for both the dominant and the second most dominant amplitudes. Because we can obtain algebraic expressions for the GPD, we can also obtain algebraic expressions for the charge ready. And fixing the ready to produce the experimental one, we obtain the following curves. The brown curve corresponds to having this relative weight gamma equal to 0.1. The red curve corresponds to having ignore this term, or gamma equal to 0. And the Nakanishi result in blue. So we can also obtain the gravitational form factors as the t-dependence of the first moment. So if we integrate over the x, we obtain this combination of gravitational form factors θ2 and θ1. θ2 is already accessible within our approach. No need to go beyond the club region. For the θ1, we need to ERBL region, and even more, we need to deal with the so-called D-term. There are sophisticated techniques to approach this one, but we have constructed a zone expression for θ1 based upon the soft pion theorem. So in this plot, I show you the θ2, electromagnetic form factor, and the θ1. As you can see, the mass form factor, or θ2, is harder than the electromagnetic, which is harder than the mechanical radius. Okay, now for the kaon, our Nakanishi model result produces the correct value for the charge ready. However, it is harder as compared with rainbow ladder results from Dyson-Schwinger equations. In the right hand, in the right side, I show you the neutral kaon as compared with early result from DSCs. And the pattern is more or less the same. And we have realized numerically that already in kaon are about 85% of the ready in pion, charge, mass, and mechanical ready. So as we expect, the kaon is more compressed than the pion. So I'm about to finish. I would like to discuss a little bit about pressure distributions, which are obtained from these expressions that depend upon θ1 gravitational form factor. So in the left, I have the pressure, and on the right, I have the shear. We can see from the pressure that on some domain of r equal or small r, we have a positive and large pressure. But at some point, about 0.45 Fermis, we have a flip change, a sign flip. That means that confinement forces take action and prevent the quarks from moving apart. And this zero coincides with the maximum of the shear forces, the QCD deformation forces. This is more like an intuition we have concerning these distributions. We can also compute the impact parameter space GPDs, which is like the likelihood of finding a parton with a given x at a transverse position B. And here in the left, we have the pion and the hadron scale. And after evolution, we see that the peaks broaden and the maximum drifts. So from a maximum of 3.49, we arrive at a maximum of 0.63. And the maximum, the location moves from x equal 9.91 to x equal 0.53. So the parton loses identity and contributes less to the total momentum. Finally, we can also obtain the mean square transverse extents from this integration over here. And we see that at the hadron scale, we have this expectation value as an entirely algebraic result, 2/3 of the charge-ready square. And after evolution to 2 GeV, we have approximately 1/9 of the charge-ready square. Concerning the kaon, as compared with the pion, we notice again an asymmetry induced by the mass of the S quark. Again, this is the Higgs modulation of the emergence of hadron masses. So to summarize, we discussed about a variety of parton distributions within the pion and kaon, starting with the light from wave function to compute parton distribution amplitudes, generalized parton distributions, the impact parameter space distributions, and so on. So we now have a lot of information concerning the momentum distribution, the special distribution, charge distribution, and so on. So we would like to have a comprehensive picture of the pion and the kaon. So I will end this talk by pointing out some facts, like QCDs, emergence of hadron masses, produces broad distributions in the light sector, as we have seen for the pion and the kaon. In the case of the kaon, because we have a strange quark, there is an interplay between the Higgs and QCD mass generation mechanisms. So this produces slightly skewed distributions for the kaon. The heavier mass of the kaon produces harder form factors, and the distributions are, of course, more compressed. For evolution, naturally undresses the fully dressed valence quark, and we obtain gluon and C quark content. And the evolution starting point is determined by the hadron scale from the process-independent effective charge and not treated as a free parameter. And finally, the simple expression from the chiral limit model is analytical and quite good for the pion. We can control the large K-pair behavior and perhaps puts TMDs within reach. And that's all. Thank you.
Thank you very much, Kepini, and well done for keeping on time. Are there some comments or questions for Kepini or in this presentation? Okay, Stan and Guy, you put your hands up simultaneously. Stan, go first, please.
Maybe Guy should talk first. I'll let him talk first.
Okay, Guy, take your place.
Well, mine is a minor comment or a question.
Yes.
You have this hadron scale you label by zeta h.
Yes.
And when you describe at the first slides in your talk the effective strong QCD coupling, then you have the start of saturation or the strong behavior at zeta. You take 1 GeV roughly, but for
Okay.
but exactly, but for the PDA evolution, this you take roughly at 1. What is the
It's
value?
about 300 MeVs.
Okay, so it is compatible with your PDA scale you choose for the PDA evolution. Sorry, for the PDF you choose for the pion. Yeah, you choose the same value, about 0.3. Yes, so they are compatible with your model.
Actually, I had some backup slides concerning these issues.
Good.
Let me. So the idea is that we have the GLAP evolution equations over here. And the idea is that instead of having leading order next to leading order evolution, we take these expressions like the leading order expressions, but instead of putting the perturbative running coupling, we use the process-independent running coupling. So if you think about the perturbative QCD coupling, you will have the Landau pole. So now we take the process-independent effective coupling with some particular representation that recovers the perturbative coupling. And if we evaluate the process-independent coupling at lambda QCD, where the Landau pole is, we obtain a mass scale. This mass scale is like a screening mass that tells us that the coupling will arrive at its, let's say, conformal domain. And this is eventually what we identify as the hadron scale.
Mm-hmm.
So we put this hadron scale into our evolution equations and claim that it is some sort of all orders evolution equations for the lab.
Mm-hmm. But isn't it too small a value? I mean, because one would expect a priori that this scale would be like 1 GeV, like the proton mass. And in there, Alexander Der and et al., this scale is very well defined, obtained about 0.99 or something like that GeV. So it's larger, and there is a very fine matching between the two regimes in this. Of course, it's a different behavior, but anyhow, I was wondering if this scale is just too low, 0.3 instead of 1 GeV. And well, they have quite different values. But that was my comment. Thank you.
Okay.
Okay, thank you, Guy. Stan, please.
Yeah, very nice work. It'd be interesting to compare all your results with the light frontallography results. You know, there's a whole new way to do all these dynamical quantities that you predicted with light frontallography, which is the duality with ADS space and the dilaton in the fifth dimension. And then you get the running coupling, you get all the spectroscopy of the hadrons, the mesons, the baryons, when you combine it with what's called superconformal algebra. And it also has chiral symmetry built in. So one of my questions to you is that I haven't heard you talk about is if you look at the pion mass as a function of the quark mass, and you have the Gelman-Oakes-Renner type of formula, do you reproduce that behavior that m pi squared is effectively linear in the sum of the light quark, mu and plus md? That's built into the light frontallography work, and I'm just curious whether you can recover that as well.
Okay.
Because there's so much similar. There's so many things which are similar.
Yes, in this particular case, since we are dealing with a model Bethe-Salpeter wave function, we take this mu and ms as constituent masses. And the specific values are motivated by solutions of Dyson-Schwinger equations with sophisticated truncations. So, for instance, the U quark constituent mass takes a value of around 310 MeVs, and the strange quark is 1.2 this value. So,
but my question was
the quark masses enter. Yes.
My question was whether
the quark masses enter like parameters, not precisely.
That's fine. My question: do you see the standard result that m pi squared is linear in the quark masses? I didn't hear you discuss that famous result of the chiral symmetry.
Yes, yes. The reason is that in this case, the quark masses are like almost free parameters. So no, we haven't really
No, I
sketched
don't.
the evolution.
Analytically, no, my question is an analytic question. Do you see analytically that m pi squared is linear in the quark masses? That's
I think I'd better intervene here because it's not going anywhere. So the answer to your question is yes, Stan. And
Okay.
Capeni is failing to grasp what you're driving at. The point is that Capeni has developed in what you might call interpolations of solutions to the gap and beta-Salpeter equations. And those equations themselves guarantee chiral symmetry and the pattern of dynamical braking. So simply put, the answer is yes.
I might just add one thing is that one wonderful trick is called superconformal algebra, which allows you to do both mesons and baryons with the same formalism. And it really works. It describes why the meson trajectories and the baryon trajectories have the same behavior, the linear with the same slope in N and L, and how they're related to each other, how you can relate meson masses to baryon masses, and then the structure of the hadrons, the mesons and baryons that become related to. And I think you could implement that into your formalism as well. So I just wanted to mention that. Also, you see
at the moment. Yeah, at the moment, I'd just like to ask, are there any more particular questions for Capeni? Otherwise, we'll move along into discussion and then we can deal or address those points you made, Stan. Anyone have anything else concretely for Capeni? No, perhaps not. Then Capeni, thank you very much.